Good morning. So we are starting this topic today, the semiconductor memories, which I just introduced in the last class. The first one, which I will discuss, I'm sure it has been discussed also in earlier classes, called non-volatile memories. Usually, these are called in semiconductor ROM or read-only memories. Read-only memories. These read-only memories, there are two types. One is, as I told you, that one is that available during the is made during the manufacturing itself. You just tell the company what kind of memories are to be stored permanently, so they make it and supply. On the other side, or on the other hand, you can also personalize some kind of memory. That means you can program them, and these are called programmable memories or PROM. The other version is called PROM or programmable memories, and these programmable memories were not easily erasable earlier. But now, with the technology and technological advancement, they can also be electrically erased. So electrically erased and electrically programmable, both kinds of features are there in today's ROMs. These are called EEROMs. Let us first start with the most primitive ROM, which is called ordinary ROM, which are made during the manufacturing. As you know that any memory should have a decoding circuit. A decoder is called decoder. And then, of course, the memory or the encoder. This is the encoder. This is the basic block of any memory. And as you know, we apply the binary input here. I can call them A0, A1, etc. A, say, n minus 1. It is an n-bit system, so you are applying n-bit input data, and that produces at the output of the decoder the decoded signals, which has got a number of bits. This can call say Z0, Z1, and similarly this is equal to Z n m minus 1, where m is equal to, as you know, 2 to the power n, that is standard. And at the output you get the so-called bits, which form the word. I'm calling that W0, W1, etc. Say W. Say it may be an 8-bit or 16-bit, whatever it may be. So that's the kind. These are called bit lines, and we shall be coming across that, bit lines, word lines, address lines. This is the plain basic or basic block of any memory. And in read-only memory, this encoder is a permanent set. A permanent read-only memory. This encoder is just made during the manufacturing process. The most simplest kind of memory, read-only memory, came during the bipolar age, when the technology was dominated by bipolar technology. These are called diode ROMs, simple diode ROMs, diode array ROMs. Diode array ROMs. Simply what you do, you have a number of like this. And then these are the output bits, call it W0, W1, W2, W3, and then we have a number of columns. Call it Z0, Z1, Z2, Z3. So these are the decoded signal. Decoded data input, and then what you do, just at the intersection of each row and column, that means this point beneath them, there is a diode. Simple PN junction diode. But these diodes will be connected or not, that depends on what kind of data we are storing. For example, suppose I just connect a diode here, maybe one diode here, maybe one diode here, maybe one diode here. Then when the encoded input Z, let us consider Z0, Z1, Z2, Z3, and the corresponding words are W0, W1, W2. These are the bits, output bits. So when you are applying a decoded signal like this, what will be W0? You see that these three are 0, this is 1, but this is unconnected. So W0 will be at 0 potential, because all these word lines are ultimately terminated to pull down to ground through these resistances. They are pull down resistors. So this will be simply W0 will be 0. What about W1? Again, here I have connected 1. So these are, again, this will be 0. What about W2? 0. And what about W3? 1. So as you apply at the input this decoded data 1, 0, 0, 0, then you get out of the system this particular word which is 0, 0, 0, 1. Okay? So if you go on now applying the next signal 0, 1, 0, 0, as you know, this is the kind of output you can get. You get from out of the decoder in standard memories. This is the kind of decoder which is used in standard memories. You apply the binary input and you get at the output this kind of data. 1, 0, 0, 0, 0, 1, 0, 0, etc. Only one digit is 0, the other 1 is the other side 0. In this case, what will get? What about W0? 1, because this is 0, this is 0, this is 0, but this is the kind of signal is connected. You have applied a 1 here, so that 1 is available at the output. Please remember the kind of configuration what I have seen and I have shown. This, you know that our input signals are being loaded, but you can prevent it by using inverters at the input. So you are getting 0, this is 1. What about the other two lines? This is also 1. Third line, also 1. Am I correct? When you apply 0, 1, 0, 0, sorry, 0, 1, this should be 1. And W1, I'm sorry, I'm just 0. And this 2, I'm sorry, just by mistake I've shown it. This must be 1, 0, 1, 1. Similarly, 0, 0, 1, 0. What will be the thing? 0, 0, 1, 0. Must be 0. Next, this is 1. Next, 0. Next, 1. Similar way, 0, 0, 0, 1. You get at the input, at the output, 0, 0, 0, 1, 0, 0, 1, 0. You just see whether there is a diode in the particular column or not. Say only in W2, in the intersection of W2 and Z3, there is a diode. So here I have a 1, other all bits are all 0. So this is the simplest way of storing data in the bipolar technology, which was used very long time ago. And as you know, the diodes, etc., consume lot of current. You know, each bit, each decoded data, decoded signal has to supply lot of current. Because these are diodes, straightforward it is loading. It is these resistances which are controlling how much current is being drawn. But this is not a very good choice. Therefore, what I can do, in place of, that was the second thing done in bipolar technology, in place of these diodes, they put transistors. In what way? Just like this. For example, the second step was, let me show only the first line. I am showing only the first line. 1, 2, 3, 4 things are there. At this point there is a diode. In place of diode, I will now connect a transistor like this. You just see what I have done. Similarly, maybe I can show the second point also. I needed transistor here. This was a bipolar transistor version of ROM. What is the advantage in it? As compared to the simple diode array, what is the advantage in it? This is an array of transistors. What is the advantage in it? Is there any advantage or there is disadvantage? What is your comment? Because base current is always much less than the collector current. You know that you are supplying from the input only the base current, which is beta times multiplied from the BCC supply, and then you get an output at the here. So your loading of the input decoded signal is much less here. Because in earlier case, you had to supply the full current. This Z0, Z1, Z2, Z3, etc. They had to supply the full current. Now they are supplying that the current divided by beta, that 1 upon beta times the actual load current. Beta being the transistor current gain. So naturally here, and another thing, as you know, I think I have mentioned earlier, in the technology, the diodes are not produced in the conventional by one junction. What is the way of realizing a diode in technology, bipolar technology? By shorting the collector and base. That means you make a transistor, shorting the short collector and base, and between that shorted collector base and the emitter you have a diode. Do you tell me, do you know why it is done? Why it is done? You could use normal PN, just a PN junction which was much simpler to fabricate. You don't have to make another diffusion, etc. And you could use it that diode, but in technology, particularly for such applications, we don't do that. We make a transistor and short the collector and base. What is the advantage in it? You know, we are sacrificing space. Transistor means the number of levels of fabrication, number of diffusions. So you are sacrificing space. Storage time. In fact, as you know, the diode also suffers from storage effect. But if you short circuit the collector base, it gives a minimum storage time compared to any other config. In fact, it can be shown. Because of the minimum storage effect, that means that these such diodes will be of much higher speed than conventional diodes. The other combination, you could just make emitter based short circuit and color. That is also not popular. One can show by analysis as well as by experimental. You can do the experiment yourself in the lab. You just take a transistor and connect the various pins and go on measuring the storage effect. And you will find it is the collector based sorting. Shorted diode gives a minimum storage effect, and that is why it is so. Therefore, be it this one or that, the other one, always you are making transistors here. At the intersection of each node, below each node, there is a transistor. So space-wise, there is no benefit here with respect to this. Only thing here, you are using the transistor as a diode, and here you are using them as transistors. And therefore, this one definitely is a much superior step forward for the realization of bipolar. But then, as you know, the MOS technology came. You can really replace these diodes, these transistors, by MOSFETs. You can put a MOSFET, but that is normally not done. What we do? We never use resistors in MOS technology. In MOS technology, we never use resistors because resistors unnecessarily occupy a lot of area. We use all, so therefore, we shall do exactly the same thing which we did in the realization of PLA. You will find that a MOS ROM is nothing but the AND plane of a PLA, is equivalent. A MOS ROM is nothing but the AND plane of an NMOS PLA. That means you just do the following. In the other case, instead of showing, that means here, instead of pull down, here what I have done, resistances have been shown in the pull down side. I will not do that. I will just do the reverse here. These are VDD line, and only thing you do is, say at this point, but here you will get the complement of the actual data. That is how you have to design this thing. Etc. And therefore, NMOS, this so-called ROM, is nothing but is equivalent to the AND plane of a PLA, standard PLA. What you do at each node there is a MOSFET, and you just connect or do not connect. That is up to you. So how the ROM is programmed, therefore, what is the method of programming a ROM? If you have understood these three things, the bipolar, the diode array ROM, the transistor array ROM, and the MOS array ROM, how to fabricate them, how to program such a ROM. You cannot do it here in your lab. What you have to do, you have to produce a data in a suitable format which can be understood by the manufacturer for making what? The masks of what? Contact holes, number one, and metallization. And then it is an easy task. Therefore, these ROMs are personalized or programmed by the manufacturer with the data given or supplied by you. What are the applications of these ROMs? Where are they used? These ROMs, there are a lot of applications, as you know. Can you tell me how are they are used?
Because there are control devices.
Anywhere in this, whatever, wherever, say for example in your calculator, how does it calculate so quickly sine theta? Yeah, it has got a stored lookup table kind of things. Okay, it does not calculate in the series and all this thing. It would have taken a lot of time. And these data are stored permanently in the ROM inside. There is no MAC tape and nothing. It is a calculator. It is a small thing. So there are hundreds of such applications where you have to permanently store some data which are all very important. Any software, as you know, we say that there are software cards. In a computer, in a PC, there are some software cards. What are these software cards? Nothing but ROMs. Nothing but ROMs. But certain cases where there is a provision for these ROMs which can be programmed. Today, that is not. And this programming there can be done in two ways. Either use a programmable ROM. Of course, there sometimes programmable ROM is quite expensive. Or you can use RAM with a backup battery. There is a small cell, so you program it and keep it. The cell is always on, the battery is always on. If due to any reason the cell, then you have the program to reprogram it. And that is the least expensive. And that is done in many practical automatic systems. All microprocessor control systems, as rightly mentioned by you, they are always, instead of using ROM, they use a RAM with a battery backup for programming permanent store. So that's the method. So this is what is called simply a ordinary ROM. Now, these ROMs, as you know, should also be clocked. Let us see what is the clocked version of a ROM. Clocked in ROM. Something like this. Simple example I'm giving. I have drawn it in the reverse, in the 90-degree rotated fashion. Then suppose what you do, say you connect transistors like this. Say in this location 1, maybe here 1, or maybe it's here 1. Like this. Let me show on here also. Again, this clocked ROM is important particularly for synchronous operation as well as for reducing the power dissipation, as you know. So what you do when phi 1 is at phi 1 and phi 2, I think you have drawn it. In this case, there must be a double number of columns. Column or rows, of course, I have interchanged between the earlier diagram and this diagram. Columns and rows have been interchanged. You have noted perhaps. And so-called number of columns is double, or it could be reduced to less because these lines could be given in different way. As you have seen earlier, it is equivalent to distribution of ground lines. What I have done, I have used, this is nothing but the so-called clocked ones. This phi 1 transistor, this set of transistors are used for precharging the output nodes, the so-called bit lines. And phi 2 is used for evaluation purpose. So when phi 1 is high and phi 2 is low, non-overlapping clock, as you know. So these transistors are on, all the bit lines are charged to 1, and then during this time the inputs come and get stabilized at the input of all the transistors located at the respective nodes. And then when phi 2 is high, and automatically phi 1 is 0 then, as you remember. So you get the output proper in the appropriate place. So in this case, you can easily write down what would be the truth table of the kind of data which is stored here. So whatever I have discussed so far, these are nothing but ordinary ROMs which are gradually becoming outdated today. Ordinary ROMs are gradually becoming outdated today. And I have discussed the ordinary, starting from the bipolar to the intermediate. These are clocks, which is very useful, of course, as you know. But as you know, that things have changed during the last 2 decades, and there have been many techniques for programming ROM, electrical. In the bipolar side, 2 things have been done. One is fuse links. Fuse links. And for the fuse links, earlier people were using nichrome. But now the material is polysilicon. And there are recent ones, these are called anti-fuses. Where polysilicon is being universally used with a very thin oxide, which I have discussed, I think, very quickly in some earlier class. This is used for producing open circuits whenever needed, and this is used for producing short circuits whenever needed. So what you do, for example, let us consider the bipolar case. Remember, there are 2 options. One, this is your Z0, and this may be W0. You are using a diode. What you do, in series with the diode, you connect a fuse link. This is a fuse link. I have actually drawn it like this. You see that at all intersections, at all nodes, this connection is there. It is not. So therefore, when the chip is available to you, all the diodes are connected via the fuse links. So there is no scope any unconnected diode. Only thing what you have to do, you have to apply at Z0 for addressing the, for programming, not addressing, for programming the memory. What you have to do? This, for example, I want to create, the diode is there, I want to remove the diode. What I do? I search it out, by a suitable, addressing technique. Then momentarily apply a large voltage here for a short time. Fuse gets blown off because of the heavy current, and you get the off. That means the normal. So wherever needed, I remove the diode this way. I remove the diode connection, not remove the diode. I remove the diode connection this way by momentarily raising the voltage at the particular node, particular input, decoded output. There must be switches, that is a standard technique in MOS, in memories. So which will isolate from the main decoded output and apply a large bias for a short time. And the current will flow over current, and if the current is above the so-called fusing current, as you know, 3 ampere fuse, 5 ampere fuse, but one cannot have 3 ampere fuse here. It should be the fuses must operate at current levels less than ampere. Usually in early days, it was typical to have fuses operating around 500 milliampere current, particularly in the days of nichrome fuses. Nichrome fuses, very thin nichrome films in the form of resistors. These are nothing but nichrome resistors, but nichrome is that the material is used for making thin film resistors. It has got a resistivity intermediate between a good metal and semiconductor. So this is a very good material, but it was found that nichrome normally takes a lot of power for fusing, and thereafter came polysilicon.
If the bias applied between Z0 and W0?
No, actually you have not, this thing is there. This thing is there, the same circuit.
But then so the entire line will fuse. All the dials in that line will fuse, which your high voltage to Z0.
Yeah, that is what I shown. There are methods of so row selection, column selection. That I am not going. That we shall discuss in more detail during that RAM, etc. It is more important. There must be, as I told you, there must be some way for individually selecting a particular node and apply the power. Just as it is, it will not work. But if you want to do the same thing for the whole column, you can do. That's up to you. It is up to your choice. Sometimes we have applications like that. As a block, we can program. It is also done. And then instead of this, you could do also. But here, actually, you know that lot of power you have to supply through Z0. What you can do, the same thing you can do otherwise by using transistors, as you have remembered. This is Z0. So apply a reasonably high bias here, gate bias, so that the current is above a certain value which fuses off this fuse. Polysilicon fuse length, when it was by research it was developed, it was found it is a very good alternative to the kind of old fuse links which were occupying large area. Not only they were occupying large area, they are occupying a lot of power. They needed a lot of input power for fuse off. But thereafter polysilicon fuse, it was found that it can be made in a very short form, and the current rating or the input power, input energy requirement is also quite less using polysilicon fuse links. I am speaking of fuse links. But today antifuses have come. I think I have told you that antifuses are nowadays widely used for programming, field programmable gate arrays, full programmable PLAs, etc. Okay, and they can also be used for programming ROMs. But EROMs have been advanced to such an extent that all those techniques are now gradually getting obsolete. These techniques were good, but they are becoming obsolete. And bipolar technology nobody uses today for realizing a ROM. Its density, capacity, etc. is very high. Its power dissipation is very high. Therefore, bipolar is now out of the question, excepting for very special requirements where we need maybe very high speed, where we may need perhaps an environment where MOS does not work, bipolar works. So in space application, certain very specific application where there is a lot of radiation which affects MOS circuitry but does not affect bipolar circuitry. Therefore, some applications are still there of these fuse links, but otherwise this is totally obsolete nowadays. So we have to now see that what are the other alternatives. And for the electrical programmability, electrically programmable ROM, these things are called PROM, P-R-O-M. Then electrically programmable ROM, also there are two names. One is simple PROM, which is difficult to erase, but can be erased by ultraviolet irradiation. Or there are certain things where both programming and erasing can be done electrically. The first one, simply for writing the memory and not erasing out, which is not, we use a device called, I think, I faintly remember that it was discussed also in my device course very briefly. A device called FAMOS, or floating gate avalanche MOS. So floating gate avalanche MOS, FAMOS, was being used. What is it? I'm just quickly showing you. Basically, the device is like this. Sorry. Etc. This is source, this is drain, and this is the floating gate. This is floating gate. These are the ordinary N MOSFET, okay? It's an ordinary N MOSFET. And suppose it has been made in such a way that it is a depletion mode device. That means normally on. Between drain and source, it can be done by channel doping. I think I've told you earlier. By channel implantation, I can arrange it in such a way that it is a depletion mode device so that it is normally on. Okay? Now what you do, between at the drain, you know, here you just see the difference between an ordinary MOSFET and this one is that the gate is totally surrounded by a very high quality dielectric. And this gate material is polysilicon, heavily doped polysilicon, N plus or P plus, variations are there. Let me not go into the device details. This is a heavily doped polysilicon, and as the advantage of polysilicon is, if you oxidize, it is all immediately covered by a very high quality oxide. So after the formation of the gate, by the usual technique, you oxidize the polysilicon, so it is covered by a very high quality insulator. So from all practical point of view, this polysilicon is surrounded by an insulator which has got a resistivity above 10 to the power 14 ohm centimeter. It's a very, very high resistivity, please remember. Above 10 to the power 14 ohm centimeter. almost an ideal dielectric. So if somehow any charge goes there, it will be stored there for very, very long period of time. Some people say 100 years. It depends, on the technology. I have to introduce some charge here so that the behavior of the transistor changes. As I told you, if I do not do anything, the transistor is on. What I do now? I apply a momentary high voltage at the drain for a short time, which causes the avalanche breakdown of the drain substrate junction. Is it all right? Have you understood what I said? For normal operation, suppose it is 5-volt operation, okay, and that is okay. On the up to 5 volt, this device remains on because it has been designed to be working under depletion mode. That means always there is an inversion layer. Under normal situation, there is an inversion layer which connects the source and drain. Therefore, the device is on. But I want to make it off. What I do, for switching it off, again permanently or at least semi-permanently, I apply at the drain with respect to the substrate a momentary high voltage for a short, you have to adjust the duration of the pulse, a single short pulse or a bunch of pulses, either a single short pulse or a bunch of pulses with adjustable duration and height. Height should be sufficiently high so that there is avalanche multiplication and almost near avalanche breakdown in this. So what will happen as a result? A lot of current will flow. And if you look at the, that always there will be a little overlap of this gate over. That is what I asked you, discussed this point earlier. In other, it becomes an enhancement mode device. This is necessary. And therefore, as you apply a large bias at the drain with respect to the substrate, just at the surface, the lines of force will shrink like this. Here the lines of force is like this, but at this cycle there will be a lot of lines of force bending. This is called shrinking of lines of force at the edge. That happens, as you know, the electromagnetics you have studied. When you come to the edge of a boundary, there will be the bending of electric. So what will happen as a result? There are a lot of electrons now going from P to N. Okay, and there are only few holes because the N plus diode means N plus side are very few holes are there. Whereas P side there are many minority carriers, electrons. So these electrons, during their passage from substrate to the drain, some of them will also follow the lines as indicated near the surface. So what will happen? If you keep this offside thickness quite small, these highly energetic electrons, some of them will be able to reach the gate. Some of them, while this will be due to the tunneling. This normally the floating gate, this offside is very thin, so that there is a possibility high tunneling transmission ability, probability is there. So what will happen? A good number of electrons, depending on how much voltage you have applied and how long you have applied that voltage, okay, I can transfer a sizable number of electrons, a good number of electrons, a controllable number of electrons from the substrate into the floating gate. But as you see that I apply it only for a short time. So after the voltage is removed, the electrons are stored there in the floating gate. And what will be the effect of these electrons? They will repel the electrons. Here inversion layers are electrons. With an nMOS, the inversion layer consists of electrons. So the negative charge which is stored at the gate, that will repel the electrons from the surface, from the inversion layer, and turn the device off. As I said that it is already designed to be a depletion mode device, means inversion layer is there. But with the presence of the electrons which are now transferred after the application of a large drain bias for a particular amount of time, this electrode which becomes negatively charged repels inversion electrons here, inversion carriers here, and that's how it transfers the device from on state to off state. That is very simple. Therefore, what I do in the so-called MOS array, at every point, I connect such a transistor. Only thing what I do, that I have to, you know that here of course the arrangement should not be exactly like this. It will be more or less something like this. You know that I have to connect the transistor or do not connect. Either you connect the transistor, I have to make a node here or disconnect the node. So I have to connect this transistor accordingly here. Only thing you apply a certain voltage for a required amount of time to create a open circuit, short circuit to open. It can be designed in the reverse fashion also. I can make it in such to work in such a way, particularly with PMOS, it is a very simple task. You can design it to work in enhancement mode so that it is normally on. It can be designed like that. And by applying a reverse voltage, I can just do the otherwise. That means I can bring in, I can store, I can actually bring electrons or holes, whatever the inversion KDS, from the substrate to the surface. That's how I can make the device on from off to on or from off on to off, whatever is possible. But what is the drawback of this kind? This was very earlier. Whatever you meant by a electrically programmable ROM, EEPROM, the device was this one, a simple FAMOS with a floating gate. What's the disadvantage of this? Usually, there are two pinpointed disadvantages. One is that the programming takes a lot of power, because it is such a mechanism that you have to create avalanche multiplication of this junction. So for programming, you need appreciable amount of power. And secondly, erasing is difficult. There is you cannot erase it so easily. This one cannot be erased so easily. What is the technique normally used for erasing this device? To remove the electrons which are charged, which are stored in the floating gate. What is done? You expose it to very short wavelength radiation, ultraviolet, or sometimes even still shorter wavelengths. X-rays, gamma rays, and all these things are possible. Usually ultraviolet, deep ultraviolet radiation. So by that photo-excitation process, electrons can be removed from the floating gate into the substrate. And that I think you have already, some of you have done, and I do not know whether you use project. Earlier students used to do that. After programming, whenever there is a need for reprogramming, just put it, there are certain lamps available in some of the labs. You just put under the lamp, keep it for half an hour, 1 hour, and again you can use it for your work. And that was the old technique. But as you know today, things have changed. Sorry, I think time is over. So I'll stop here today. Thank you.